When you read in the newspaper that scientists have found the Higgs boson or gravitational waves or a cure for AIDS or a cure for COVID-19 or whatever, you must always understand that that statement has been made probabilistically. Nobody can say for certain that all COVID-19 patients will be cured by this vaccine or that vaccine. There is a chance. The bigger the chance, the more reliable the vaccine. So today we're going to get into a quantitative estimate of what that should be. And then this will take us into the concept of cumulative distribution functions. And all this will be for discrete probabilities. However, our next step will be to extend this to continuous probabilities. So, for example, take a particle that's confined between these 2 points over here. So it moves anywhere between here and there, but it could be at an infinite number of different positions with different probabilities. If you ask what is the probability that it is exactly at one point, the answer is 0. But you can ask what is the probability that it will be in a certain interval. And so that will require a little extension of what we've studied before. And that, of course, is the subject of this lecture. Earlier, we talked about a random variable x. Now, x can be totally random, it can be mostly random, or it can be well-defined, or it can be said to be certain. So there are different degrees of randomness and different ways of measuring randomness. What we shall do in this lecture is look at variance and standard deviation, which are measures of how random a distribution is. Let's begin with a distribution, a probability distribution, P of k, and this x over here tells you that the random variable x can take different values of k. Each of those has a certain probability. So the probability that x is equal to k is this, and of course all probabilities must add up to 1. We had also earlier on discussed what it means to take the average of x. So you take the value that x can take, k, and you weight it with its probability. And then you make a sum over all possible values of k. What about the random variable x squared? Well, then you can extend this to any value of n. All you do is you take k raised to the power n weighted with the probability. So this over here is called the expectation value of the nth moment of x. The most important are the expectation of x itself and of the square of x. Again, I remind you about notation. Sometimes I use the expectation value of x and sometimes I use this, the brackets with x in between. Definition. Variance is defined as the expectation or average of this quantity. So this is x minus the average value of x squared. Why squared? Because the value that x can take can be lesser than the average or greater than the average, and if it is equal to the average, then of course this quantity is 0. In terms of this, the standard deviation, which is called sigma x, this x denotes that it's the random variable x that we are talking about, is simply defined as the square root of the variance of x. The standard deviation sigma is actually what is quoted in various experiments or processes. Of course, while its meaning is perfectly clear from here, there is still a simpler way of expressing the standard deviation, so let's get on to that. Look at the variance of x, that's just the definition above. Instead of this x over here, I have k, the value that x can take weighted by the probability. And remember that this thing over here, average of x is a number. It doesn't depend upon k, whereas of course k is being summed over here. And everything is weighted by the probability distribution. Now let's do a little bit of algebra. The first term over here, when we open out the square, is obviously k squared times p. And this is nothing but this quantity over here, the expectation value of x squared. The second term, as we open out the square, is this minus 2 average of x, and then we have the summation over this k times p of k. I could take out this quantity, average of x, because it does not depend upon k. The last term is, of course, the easiest, and that's just x squared itself weighted by the probability. And now this sum over here, we see from here, is equal to 1. Now, obviously, this over here is nothing but the average value of x itself. And so what we have is the average of x squared minus 2 times the average of x multiplied by the average of x. And then, of course, the same thing over here. So then you get this quantity over here. That, of course, is the variance. Let me make this more explicit. Suppose there's a very strange kind of die. It always lands on the face 5, never on the face 1, 2, 3, 4, or 6. Only and only 5. So the probability of having a 5 is 1. The probability of all other numbers is exactly 0. So then the average value of x is 5 times 1. How did I get this? Just using this. When k is equal to 5, this is equal to 1. If k is equal to anything other than 5, then this is equal to 0. So the average value of x is 5 into 1. The average value of x squared is 5 squared into 1, which is 25. The variance of x is therefore 25 minus 5 squared. That's from here. And of course, the standard deviation is equal to 0. Now what that means is that there's no randomness here. This die is always going to land with the face 5 up, and so the variance disappears and obviously the standard deviation disappears. Of course, this is a highly unusual situation. Let's go to something which is more normal. This time, take a normal die. Then it has equal landing probabilities, equal to 1/6. It can land with the face 1 with probability 1/6, the face 2 with probability 1/6, and so forth. And if you just add these all up, well, then you'll get 21/6, which is 3.5. This, of course, is the average number after you throw the die a sufficiently large number of times. What about x squared? Well, that's perfectly simple. All you need to do is square the value of k. So this was k squared. And now this is with probability 1/6. The 2 is with probability 1/6, and so forth. Now that you just add these, and you can just do this using a piece of paper, you get 91/6. That converts into 15.17, and so if you take the variance, well, that's this number, 15.17, minus 3.5 squared, that gives you 2.92. Take its square root, and that gives you 1.71. So this tells you the spread in the random variable x. Remember, earlier we took that die which always lands on one face, in which case sigma was 0. Well, let's take another random variable. And this time, I'm going to take two normal dice. As the random variable, I will take the sum of the numbers that appear on each throw. So, for example, if I throw the die once and I get 1, and the second time I throw it, I again get 1, then the random variable takes the value 2. What is the probability for that? Well, the probability of getting 1 the first time was 1/6. The probability of getting 1 the second time was 1/6, so multiply them together and that's 1/36. What's the probability of getting 3? Well, it'll be twice as much because I could have gotten 1 the first time, 2 the second time, or I could have gotten 2 the first time, 1 the second time. So there are twice as many events that give me 3. And of course, the probability then becomes 2/36. And similarly for 4, 5, 6, 7, 8, 9, 10, all the way up till 12. In the case of 12, then the die has to land the first time with a 6, the second time also with a 6. The probability of that is 1/36. Now let's calculate the average value of x, and that's easy enough. What we need to do is take the value of k. Well, k here is 2, then it's 3, then it's 4, 5, 6, 7, 8, 9, all the way up till 12. We weight them with the probabilities. The first one is weighted with 1/36. Getting the number 3 has probability 2/36, and so forth. So we have 2 into 1/36 plus 3/2 into 36 plus 4 into 3/36, and we keep going. You can just add these numbers up and you will get 7. Now it should be perfectly clear what we need to do in order to get the average value of x squared. And that means you simply square this, like over here, and you square this, like over here, and then you weight them by the probabilities, and the probabilities are exactly the same here. Simply add up these numbers all the way from 2 up till 12 squared. You'll get 329 divided by 6, convert that into decimals, and you'll get 54.833. And the next thing to do is take the difference between this and the square of this. You'll get the variance as 35/6. Take its square root and you get 2.42. All these things you can do with the help of a calculator. But wouldn't it be nice if one could have a simple formula for at least some probability distributions? And we go to that next. In this solved example, I will find the average value of x and the average value of x squared for the binomial distribution which we had talked about earlier. Now, just to remind you about the binomial distribution, this is the probability that the random variable x will take the value k, and that's equal to this. And now just a quick reminder of how this was obtained. So think of a coin that has probability p for landing on its head, and therefore 1 minus p for landing on its tail. We throw the coin n times, and we ask what is the probability that the coin lands on its head, k times. Well, that probability p has to be multiplied by itself k times, so that's p to the power k. But of course, if it landed on its head k times, it landed on its tail n minus k times. And so therefore, we have the product of this probability, that of having k heads, and the probability of tails n minus k times multiplied together. But then we have to look at how many possibilities there are of getting k heads in n throws. And that's this binomial coefficient n choose k. Anyway, we've done this before, and we can use the binomial theorem The binomial theorem, in fact, tells you that if you sum over all values of k, then the probabilities add up to 1. I'm going to take this very innocent-looking equation and do a certain very sneaky manipulation on it. I notice over here that p is a variable with respect to which I can differentiate. And if I differentiate both sides of this equation, like now, then clearly the right-hand side is the derivative of a constant and hence is equal to 0. Now I can start differentiating what is to the left side. And so, by differentiating p to the power k, I will get k, p to the power k minus 1. That is, every time I differentiate p, its power is reduced by 1. And so I have p to the power k minus 1. So far I have not differentiated this other one over here. That remains the same. Next, I'm going to differentiate the p which is inside over here. And because of the chain rule, when I differentiate with respect to p, I'm going to get a minus sign over here. That's very important. That minus sign comes over here. Again, I get n minus k coming out. That's over here. And the power of 1 minus p gets reduced by 1 because of the differentiation. Now here there's something very, very obvious that's staring you in the face. Here is p to the power k minus 1. Well, can't I write this as p to the power k divided by p and then take the p outside of the summation sign because it doesn't depend on k? In that case, I'll get k times p of k, which means I get the average value of k, and this is the p that I took outside in the denominator. So this term over here is obviously this. Exactly the same can be applied over here. So here we have to take this extra minus 1 power over here. That's a 1 over 1 minus p, which I can take outside over here, and the rest is just the average value of the quantity n minus k. Now the average of n is of course just n itself because it does not depend on k, and the average of k, hey, what is that? That's the average of k. So I just need to now simplify this, noting that this is equal to 0. The easiest way is just multiply by p into 1 minus p, in which case I get 1 minus p into the average of k, this term over here, minus np plus p times average of k. Now this and this term cancel, and I get this lovely simple result that the average value of the random variable x, or what we denote as average of k, is simply equal to n, the number of times that I've tossed the coin, multiplied by the probability of getting a head. This makes a lot of sense, doesn't it? Because we could have defined probability as the number of times we get a head divided by the total number of throws. So you couldn't have hoped for a simpler formula. Well, now we're going to push our luck further. And so watch carefully. Now I'm taking the derivative of what we had earlier, which was 0. So obviously the derivative of 0 is 0. And now I have d by dp of this equation here, which was, as I said earlier, got by differentiating this equation. This is going to be a little more complicated because now we have to differentiate p in 4 different places. There's p here, p here, p here, and p here. Let's look at each of those 4 different terms. When we differentiate this p, we're going to get 1 less power of p, so k minus 2, and k was already there. K minus 1 came down from the differentiation. The rest we write exactly the same. Next, I'm going to differentiate this p. When I differentiate this, then again I get a minus sign, which is over here. And the k is as before. This k is the same k here. But then I get a n minus k, which comes down from here. And of course, one less power. And so it's 1 minus p, n minus k minus 1. Now we are done with this term over here. Let's go to this term over here and first differentiate this p to the power k. Then we're going to get k into n minus k. There is one less power of p. Everything else is the same. And finally, I have to differentiate this p over here. So I'll get a negative sign from here using the chain rule. And so that becomes a positive sign. N minus k remains as it is. N minus k minus 1 comes from here. And then, of course, one power has to be reduced, so it's n minus k minus 2 now. We are almost there. Just a bit of simplification is needed. We see that this is p to the power k divided by p squared. And so take that p squared out of the summation sign since it does not depend on k. And so the first term here is simply this. The second term, which is over here, and the third term, which is over here, are obviously identical, and that's what will give us this factor of 2 over here. Now, look over here. Here we have p to the k divided by p, and here we have 1 minus p to the n minus k divided by 1 minus p. So we take the p into 1 minus p outside, and that's what gives you this. Inside is the expectation value of k into n minus k. And finally, this third term, this is exactly what we had for the probability distribution, except for this extra power of minus 2, and that then becomes 1 minus p squared in the denominator. Next step, well, k into k is k squared, and the expectation value of k squared is what we want. Inside is k into minus 1, and that's the expectation value of k, but we've already found that out. That expectation value of k is n times p, and so that's over here. So the first term here gives this, and similarly here we have k into n, which gives us n squared p, and here is k into minus k, which gives us minus k squared, and that's the expectation we want. Similarly, over here, you can just multiply this out and use this. You'll get this numerator with this denominator. After this is just a matter of algebra. One way of doing that is to multiply both sides of this equation by p squared into 1 minus p squared, do a bit of algebra, and we find that the average of k squared is then this thing, p squared n squared, plus np into 1 minus p. Since we are interested in finding the standard deviation, well, that's the average value of k squared minus the average value of k squared, square root of that, and so that's the square root of np into 1 minus p. Notice that this is symmetrical between p and 1 minus p as it should be. Notice also that if I take sigma and divide it by n, then as n becomes larger and larger, sigma over n will go to 0. The Russian mathematician Chebyshev discovered a very interesting and important rule. I'm not going to prove this rule, but it's something that you can easily understand. So let's ask, what is the probability that a random variable x will take a value which is between its average mu? By the way, here instead of writing this symbol average of x, I've decided to call it mu because it looks nicer. It's the same thing. So what is the probability that x is between mu plus some number m times sigma, and this m, the only thing that we require of it is that it be a real number which is bigger than 1. So the probability, according to the Chebyshev rule, that x lies in this interval is greater than or equal to 1 minus 1 over m squared, whatever that m be, provided only that m be bigger than 1. So, as I said, I'm not going to prove this, but let's try and understand what this means. Now take a distribution whose average value is mu. This has some standard deviation sigma associated with it. Here's another distribution. It has the same value of the average mu, but you can see that it is broader. In other words, it's got a bigger standard deviation sigma. So to repeat, the red dots are small sigma, that is to say, the values lie closer to the average value mu. The black line over here has got a larger sigma. You can just think of this as a large number of dots. So now let's explore the meaning of the Chebyshev rule. Let's first ask, what if m is some very large number? For convenience, call it infinity, in which case the probability that x lies between infinity and minus infinity is simply going to be equal to 1. In other words, the random variable x has to take some value on the real line. But what if we take m not to be infinity, but let's say 2? In that case, the probability that x lies within 2 standard deviations will be greater than or equal to 3/4, which is 75%. Okay, now take m equal to 3, which is 8/9, which is 88.9. Take m equal to 4, that gives you 93.7%. Take m equal to 5, and that gives you 96%. And of course, if you take m larger and larger, then you're going to get closer and closer to 1. The smaller the standard deviation, the greater the probability that x will take values close to its average. Let's try out one last problem. So we are asked to apply the Chebyshev rule to the probability distribution where x takes values -1, 0, and 1. Just these three with probabilities 1 over 2m squared, 1 minus 1 over m squared, 1 over 2m squared. So this is a fun problem. Let's apply the Chebyshev rule over here. Well, obviously, the mean value of x is simply 0 because it takes a negative value, -1, and a positive value, +1, with the same probability. So mu is 0. We can calculate sigma squared, which is obviously this. What we called earlier k takes the value -1. You square it, multiply it by the probability. Then, of course, you have 0 times the probability of getting 0, but of course that's equal to 0. And finally, 1 squared times the probability of getting 1. And so that gives you 1 over m squared. Having calculated the average and the standard deviation, the Chebyshev rule says that the probability that x will be less than or equal to 1 is greater than or equal to 1 minus 1 over m squared. And remember that m is a number which always has to be bigger than 1, and so this probability will never exceed 1. Now let's recall that the sum of all probabilities has to equal to 1, so you can use the fact that the probability that the absolute value of x is less than or equal to 1 plus the probability that the absolute value of x is greater than 1 adds up to exactly 1. And so this here translates into this, which means that we have established that the probability that the absolute value of x is bigger than 1 is simply equal to 1 over m squared. Now the Chebyshev rule applies to every probability distribution, but of course if you know what the probability distribution is, then you can sometimes get sharper bounds than that of this particular rule. The concept of a cumulative distribution function is a very useful one, and it's defined as follows. The cumulative distribution function of a random variable x is denoted by the function f with a subscript capital X of k. And of course, k are the possible values that the random variable x can take. This CDF is defined by the following relation, that the CDF is the probability that x takes values which are less than or equal to k. So the same k that occurs over here is over here. And of course, to refresh your memory, p with subscript x of k is exactly this. To understand this better, let's take the example that we had considered just a little while ago, in which k takes these values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 with the probabilities 1 over 36 all the way up till 6 over 36 and then back to 1 over 36. Now clearly, if I take values of k which are less than 2, there's a 0 probability for that, and so fx of k is 0 for all values of k less than 2. But if we include k equal to 2, well then fx of 2 is 1 over 36. fx of 5 will be 10 over 36. So if you look at k equal to 5 and ask what is the probability that x will take values less than or equal to 4, then that is 1 over 36 plus 2 over 36 plus 3 over 36 plus 4 over 36, and that's 10 over 36. fx of 11, well, just add up all the probabilities from here all the way up till here, and you get 35 over 36. Of course, fx of 12 is 1. And what about fx of k for k bigger than 12? 50, for example. Well, the probability of getting a number bigger than 12 is exactly 0, and so fx of k, the cumulative distribution function, will remain 1 for k greater than 12. Actually, the CDF has some pretty obvious properties. So, suppose that k is 0 below k minimum, whatever that is, and it's 0 above k maximum, whatever that is. In that case, it's obvious that, as defined over here, fx of k will be 0 for k less than k minimum. It's also obvious that the CDF will be 1 for values of k which are bigger than that of k max. Now, because probability is always positive, as you go to bigger and bigger values of k, fx of k will either increase or it'll stay the same. In no case will it decrease, and hence we say this is a non-decreasing function. And finally, if you take two different values of k, let's say y and x, if you take the difference between them, then that's obviously the probability that the random variable x will take values between y and x. So far, we have been only talking about discrete random variables, but now we are going to go on to continuous random variables. There's a basic difference. In the sample space of the random variable, x has now an infinite number of elements, whereas for a discrete sample space we had only a finite number of elements, or they were infinite but could be counted. So in the probability distribution function, which we call px of x now, this x is a real number. The real numbers constitute an infinite set, but not just infinite, they are uncountably infinite. Anyway, this here is a notation. This means exactly what it meant in the discrete case. The only difference is, as I said, x changes continuously instead of discretely. Why is this important? Well, we have numerous examples, so let's look at some of them. Take an electron. It could be any distance from the atom center. And distance, of course, is a continuous variable. Or take this example. What is the chance of a particular wind speed as measured on your rooftop? In other words, here, your random variable x takes values of wind speed, and that wind speed is continuous. Or your random variable x could take values of the speed as you drive through traffic. And so again, that's a continuous variable. You could look at pressure in a gas tank, and of course, pressure can take a continuous set of values. And finally, you could look at, for example, the chance of death as a function of the number of air miles traveled. The basic point is that we are looking at functions of a continuous variable. Going from discrete distributions to continuous distributions is actually not hard, and we learned this while studying calculus. So you learned over there that if you sum over discrete values, then you can get to the true area, and the true area is got by taking an integral. Let's see how that works out. So here is a function of, let's say, x, and we want to calculate the area under it. Well, we can do it by taking this rectangle here and this rectangle here. Over here we make an error, which is undercounting because we miss out this area here. Over here we have missed out all of this area. However, if we take 4 points, well, then we're getting closer to the true area. If we take 8 points, we get closer still. And 16 points is still better. And of course, you can keep going until you take an infinite number of points, and then we will approach what is called the integral, the Riemann integral. That Riemann integral then gives us the true area under a curve. This was perfectly general, but now let's talk about probability. The probability of finding x in this interval between x and x plus dx is denoted by p of x times the size of the interval dx. And in this interval, p of x, of course, will be approximately constant. The smaller the interval, the less the value of p will change within that interval. There's a name for this, p of x, or a long way of writing this is to include a subscript here. Of course, this random variable x takes values x. Now, usually to save space, we don't write this, we write this. In any case, this is called the probability density function, and the probability density function tells you that if you integrate from a to b, that's the probability that x will be found between a and b. Obviously, if you go far enough to the left and far enough to the right, then the sum of all the probabilities must add up to 1. And this integral tells you exactly this. After all, an integral is nothing but a sum. As ever, This tells you that x certainly has to be somewhere, even if we don't know exactly where it is. It should now be pretty clear how we connect discrete to continuous probabilities. So, for example, the sum of probabilities has to add up to 1, or equivalently, the integral over the probabilities has to equal 1. If one takes the average value of x, which is denoted here as average value of k, that's k weighted by the probability p. Exactly the same thing happens over here. The average value of x is x weighted by the probability, and the probability is p of x dx. Here, instead of the sum over k, you have an integral over x. All the powers of k are done in exactly the same way. Where you have k squared, you have k squared here. Where you have x squared here, you have x squared here. And of course, the standard deviation is calculated in exactly the same way as before. So earlier it was this. In the case of continuous probability distributions, it is this. The CDF translates in the obvious way as well. Notice that here the CDF has an integral that goes from far to the left up till the point x itself. Again, all the properties of the CDF that we had explored earlier apply to the continuous function as well. There's one additional thing which is sometimes very useful, and that is if you use the fundamental theorem of calculus. So suppose I was to take the derivative of this, d by dx of the CDF here, well, that means I'm differentiating this limit over here, and the fundamental theorem says that d by dx of this is equal to the function inside the integral sign, which is p of x. In every first course of calculus, one learns this fundamental theorem. Let's take a few examples of continuous distributions. So here is p of x defined as follows. It is 0 for all values of x that are less than or equal to 0. 2x if x lies between 0 and 1, and 0 if x is bigger than 1. It is always nice to picturize functions. So if you were to plot this, to the left it is 0, to the right after 1 it is 0 also, and between 0 and 1 it rises linearly like this. It goes up to the maximum value 2, after which it suddenly comes down to 0. What does the CDF look like? We must integrate from the extreme left to x itself. The integral from minus infinity up till 0 is obviously 0, but we need to know the integral from 0 up till, let's say, some point x, which is between 0 and 1. And that, of course, is going to be the integral of 2x. That integral is x squared itself. And so, between here and here it is 0. From here to here, the CDF is x squared. And then it keeps the value 1 for all values of x which are bigger than 1. As our next example of a continuous probability distribution, look at this one. Here p of x is the exponential of this quantity here, x minus 2 whole squared divided by 2. And there's a constant up front over here. This constant has been put so that the integral of p of x from minus infinity to plus infinity will give you 1. So if you graph this, you see that at x equal to 2, this p of x achieves a maximum, and that's because you see that this is equal to 0 only for x equal to 2. As you go to the right or you go to the left, this will give you a increasing positive number, and so the exponential will decrease. And so therefore you have a graph that goes off to 0 to the left and a graph that goes off to 0 to the right. This is what is called a Gaussian distribution, and we'll come back to it later. Now, of course, I haven't told you how to do this integral. That's because this is not a course in calculus, but you can just go and look up a table of integrals and you'll see that integral of p of x dx is equal to 1. However, if I put x over here in front of p of x, and again I integrate from minus infinity to plus infinity, then I'll get the average value of x, which is equal to 2. It's quite accidental, actually, that the maximum value of p of x occurs at 2, and so is the average 2. In general, the two quantities will not be the same. Now we can calculate the average value of x squared by putting x squared over here and integrating again over x from minus infinity to plus infinity. Look up a table of integrals and you'll get this. The average value of x squared is 5. From here, you can get the standard deviation. So that's 5 minus the square of the average. So that's 1 over here. You take the square root and that's 1 again. We can also get the cumulative probability function, and that's got by integrating p of x from minus infinity to here, to x. Now, there's an x prime over here because we can't use the same x here as here. So what is being integrated over is a dummy variable. Indeed, as expected, the CDF goes to 0 as you go to the left, and it goes to 1 as you approach it from this end. So this CDF has indeed all the properties that we saw earlier for the case of discrete CDFs. Let's solve a couple of real-life examples. First, let's take a phone call whose length is denoted by the random variable x. So x takes values which are in minutes, and now suppose that its probability distribution function is 1/8 e to the minus x over 8. The reason I've put 1/8 over here is because we want the integral of p of x to be 1. We are asked to find the probability that a call will last less than 6 minutes, or at least 6 minutes, or exactly 6 minutes. Now this is an easy problem. All we do is we integrate the probability distribution function from 0 to 6. So all calls whose duration is less than 6 minutes are included in this. Doing the integral is simple because e to the minus ax is equal to minus 1 over a e to the minus ax. If we evaluate it between the limits 0 and 6, then you can immediately see that from the lower limit we get 1, from the upper limit we get e to the minus 6 over 8, which is 3 over 4. If you convert this into decimals, then it's 0.5276. Putting this in words, the probability that a call will last less than 6 minutes is 52.76%. Now let's look at part B, which says that the call has to last at least 6 minutes. So it has to be a number between 6 and infinity. We integrate the probability distribution between these limits, and we get e to the minus 3 over 4. Again, this over here is what we got over here. If you now convert this into decimals, then the probability that a call will be over 6 minutes will be 47.24%. And of course, the sum of A and B has to be 1. So either a call is less than 6 minutes or it's greater than 6 minutes. But what if it's to be exactly 6 minutes? Well, the answer for that is 0. And that's because we are asking for something very, very exact. In other words, we are asking what is the area under e to the minus x over 8 between 6 and 6? Well, obviously that is 0. A second example. Suppose we have a random variable x which has the probability distribution function given over here. So it is 0 for x less than or equal to 0. It's 1 over 25 if x is between 0 and 25, which means it's a constant. And of course, if you integrate p of x, then that will be 1 over 25 times the length of this interval, which is 25, and you'll get 1. And of course, for x greater than 25, this probability is 0. For this distribution, we are asked for the probability that x is greater than 15 given that x is greater than 10. Now you remember from our discussion on conditional probability that the probability of A given B was the probability of the intersection of A with B divided by the probability of B. So in this case, x has to be greater than 15 and x has to be greater than 10. So that means P of B is integral from 10 to 25 of P of x, which is 1 over 25. And so we'll get 15 over 25. Over here, the intersection of A with B is from 15 to 25. In this interval, we have x being greater than 15 and x being greater than 10. Now this integral is 10 over 25, and so we get 10 over 15 with the 25 having cancelled in the numerator and the denominator. What about the probability of x greater than 15 given x less than 10? Now obviously this is 0 because there's no intersection between the sets x greater than 15 and x less than 10. And finally, the probability that x is less than 15 given that x is greater than 10. So again, we have an overlap of the two sets. That overlap is between 10 and 15, whereas the probability that x is greater than 10 is the integral from 10 to 25. So this gives 5 over 25. The denominator is 15 over 25, and we get 5 over 15. Now notice one thing, that if I add this to this, I get 1. And that's no surprise because we've covered the entire sample space for x greater than 10. Finally, we'll see how these ideas are extended to other continuous distributions, beginning with the joint probability distribution function defined here. We ask what is the probability that x is in the interval between x and x plus dx. Dx is of course small. And y is in the interval between y and y plus dy. We define this to be p of x, y into the lengths of the two intervals, dx and dy. And this is a definition for p of x, y, the joint PDF. From this, we can get the single PDF. So if we integrate over all values of y, we get the single probability distribution function for x. And similarly, if we integrate over x, then we get the single probability distribution for y. Here's how to think about this. There's a particle in this interval, x and x plus dx, and a second particle in this interval. Now, if we do not care about where the second particle is, we will integrate over all its positions, and that will give us the probability of the first particle being in the interval dx. On the other hand, if we don't care about the first particle, then we integrate over all its possible positions, so integral over dx, and this way we get the single particle distribution function for the second particle. We can also replicate what we did for the conditional probability distribution function, and here if we ask for x given y, well, that's p of xy divided by p of y. This exactly follows the definition that we had used earlier, that p of a given b is p of a intersection b divided by p of b. And of course we can reverse this. P of y given x is this divided by p of x. Bayes' theorem is exactly as we had written earlier, except with these obvious changes. So the conditional probability of x given y is the conditional probability of y given x into p of x divided by p of y. We'll see some applications of Bayes' theorem for continuous probability distributions later.